Broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Welcome to the monthly webinar from Goldson Technology Group. Today we're going to be talking about modeling water treatment using the Contaminant Transport module. We've got a pretty big crowd today, so if you have any questions, let's hold them till the end. If you have any questions at the end, you can unmute yourself and we can answer a few questions. Otherwise, you can always feel free to send me questions directly, and my email is on the screen. So we're going to talk about the Contaminant Transport module and how it can be used to specifically model water treatment processes in a model. So in order to simulate some kinds of complex systems, we have these specialized modules. The Contaminant Transport module is one of them. And it's a specific set of tools to support complex contaminant transport simulations. What it does is it produces predictions of mass transport rates, concentrations, and ultimately impacts to human receptors. There's a lot of things in the contaminant transport module. We can simulate mixing and solubility constraints, some chemical processes such as sorption, advection, dispersion, diffusion, some simple reactions. For those who are doing radioactive waste management, we can do radioactive decay and ingrowth. I'm going to have to assume that most of you are have a basic understanding of the CT module. We've given previous webinars on this because we're just going to talk about one specific aspect of the CT module. But to start out, for those of you who are not familiar with the CT module, I'll provide a very quick review for 5 or 10 minutes, just so for those of you who are new to the Goldson CT module, you'll be able to follow along with a couple examples I'm going to walk through. So we're going to focus on two relatively simple features in the CT module that can be used to model water treatment processes. One of these is specifying treatment efficiencies, and another one is specifying solubilities and removing mass that's been precipitated out, let's say in a treatment tank. These are two very simple features that are built into the Goldsim Contaminant Transport module that were specifically put there to model water treatment. I'm also going to mention, but I'm not going to discuss in any detail, a much more complex way to model treatment. And that is integrating the chemical processes directly using tools such as Freak-C. This is an order of magnitude more complex than what I'm going to show you in these two simple processes, but I'll mention it. I'll show you some examples that we have on our website for doing this much more detailed approach. So for those of you who are hoping this is what I'm going to talk about, sorry, this really deserves 1 or 2 webinars all by itself, just to talk about how this is done. In fact, we're working on this. Probably later this year, early next year, we'll have a standalone webinar that talks about using tools like Freak-C to simulate chemical processes. But we're not going to do that today. We're just going to discuss some very simple processes that are built into Goldsim, but then can be very powerful, that allow you to model treatment in a simple but often very realistic way. But before we do that, I want to provide a quick and basic overview of the CT module. Again, just so those of you who are not familiar with the CT module will be able to follow along with the examples I'm going to show. So very quick and dirty, we'll just take about 5 minutes or so. I just want to review what the Contaminant Transport module is all about. So what the Contaminant Transport module does is it adds some specialized elements to GoldSim, a series of elements to allow you to simulate contaminant transport processes. It provides a basic framework for modeling the movement of mass through a system. You can build a very simple model, or you can build an extremely complex model. It's got some basic physics built into it: conservation of mass, decay of species, fusion, partitioning. But it's very, very flexible. So you can build an extremely complex contaminant transport model in multiple dimensions, or you can build something quite simple. We're going to walk through some very, very simple examples today in order to illustrate the water treatment. One other comment is that the contaminant transport module relies quite heavily on using arrays in GoldSim. So those of you who have just built perhaps some water management models may not have used arrays, although they can come in quite handy for those models too. For contaminant transport modeling, arrays are critical. You must use arrays. And in particular, the species that you're simulating, iron, zinc, or uranium, whatever, are handled in arrays. And it makes the model much easier to build and scale up. So when we build a contaminant transport model in GoldSim, the steps we go through is we're going to define some species that we're going to model. We're then going to specify some transport and storage media. So a medium is something like water or air or soil or sediment, clay, sand. And these are the media in which the mass itself is either stored and or transported. Then we're going to specify some transport pathways through which the mass is transported and stored. So a transport pathway is made up of media. So, a mixing tank may just consist of water. An aquifer may consist of water and sand or water and clay. Obviously, in order to build any kind of contaminant transfer model, we have to put mass into the model, so we can define some source terms, some initial and boundary conditions. And finally, once we do all this, we can also, these steps right here are going to produce, are basically going to produce masses at different locations, concentrations at different locations. In many cases, that's all we need, but in some cases, we may actually need to convert those to impacts. So for example, if I'm doing a radioactive waste management model, I really don't care about the concentration, I care about the dose. And in order to do that, I have to do another step in my model. I have to define a receptor and some pathway by which they're exposed to this concentration. We're not going to talk about this in this webinar at all. We're really just going to focus, in order to illustrate water treatment, on these first three steps. So I'll just say a little bit about defining species. I'm going to show you a few models where we just have a couple simple species, zinc and iron, let's say. But we can model as many species as we want in GoldSim. In the basic contaminant transport module, GoldSim knows nothing about chemistry. It doesn't. You just invent. I've created a species called C and another one called D. So it doesn't have any of the chemical properties built in. You're going to have to define those properties yourself. If you were doing radioactive waste management modeling, and you had the RT module, the radionuclide transport module, that particular module actually has a module that includes has an entire library of all of the radioisotopes with their half-lives and decay products and so on. But for basic modeling, the kind of stuff probably most of the people in this webinar are interested in, you're going to have to enter the species yourself. So once we do that, we then are going to define these building blocks of our transport pathways, which are the environmental media. And they're essentially, you're always going to have a fluid. Typically it's water. It doesn't have to be water. It could be, you might say, well, why, in what case wouldn't it be water? Well, one example is you could use the contaminant transport module to actually simulate the movement of a chemical through an organism, let's say a fish. It would be called a pharmacokinetic model. In that case, the main fluid is blood, not water. Physics happen to be very similar to what we're doing for a contaminant transfer module. For what you're doing, we're going to basically be dealing with water. You actually may have different flavors of water. You might have different types of water that have different properties because their chemistry is different. And then you might have a number of solids. And this is where we're going to put in the properties of the media. The properties of the media are really going to control how things move through your environmental system. So for example, your solids can have partition coefficients. So you can define how your mass partitions between the fluid and the solid. For the purpose of this webinar, the one property that we're going to focus on is the solubility, because one of the processes that we can simulate is we can force these species to actually come out of solution, let's say in a treatment tank. And in order to do that, we have to specify some solubilities for those species. So you'll see that here in the example I'm going to do shortly. So once we define these media, we then define some transport pathways, and the transport pathways are really just the parts of the system where we're moving or storing mass. And in our model, they could be they could just be tanks, right? So you might just have some mixing tanks. You could be simulating an actual engineered system that just has a series of tanks. But typically, you're going to have some ponds, and maybe you have some aquifers, some lakes, and might be a soil column. Each one of these transport pathways, we're going to define them using media. So a mixing tank may just only have water in it, and an aquifer might have water and sand in it. A pond might have water and some sediment in it, and so on. A soil column might have soil, water, and air, might have another fluid, so air and water in it. So the way you should think about a transport pathway, this is not really mathematically correct, but it's a good way to conceptualize it. A transport pathway takes some mass flux coming in, and does something with it and spits it out. And typically what it does with it is it delays it and disperses it. Typically what happens. It may actually, there may be some decay going on in here also, but we're basically going to delay and disperse things as we move through a transport pathway. So when we build a contaminant transport model in GoldSim, we're going to hook these pathways together to simulate the system, and we're going to link these pathways together via some mass flux links that say what is the process that moves mass from here to here. Typically, the process that moves mass from one location to the other is advection. We're moving a fluid, or we could actually move a solid from one location to the other, and it's going to carry with it mass. Or diffusion. We're going to diffuse mass from one location to the other. When we're simulating water treatment, you're going to see we're going to have some specialized ways to move mass from one location to the other. That is not advection or diffusion. We'll talk about that in a minute. So GoldSim actually provides a lot of different types of pathways. In this webinar, we're just going to talk about cell pathways. We're going to use cells to illustrate the features that are incorporated into GoldSim to simulate water treatment. Okay, so that was a very quick overview of the contaminant transport module. We just covered it, covered the 400-page manual in 5 minutes. There is a webinar that we did, I think, earlier this year or late last year that goes into a little bit more detail on the contaminant transport module. If you can go to our website, you'll see a link where you can see all of the past webinars and download them, the presentation and all the files we used. And of course, you can always look at the documentation and some of the examples we have online. So now let's switch to simulating water treatment. So what we're going to talk about now is specifically how do we use this contaminant transport module to simulate water treatment. So we're going to return to these cell pathways that I mentioned. So cell pathways are mixing cells. What does that mean? Well, we can put media inside the cell pathways. In this webinar, we're only going to have water in our cell pathways. Just to simplify things, we're not going to have any solids. We're not going to have any other fluids. We're just going to have water. All right, we have water inside our cell. In fact, we're just going to simulate a tank. When mass enters that mixing cell, it's instantly mixed. All right, so the mixing cell is instantly mixed. If you were simulating a lake, let's say, that had a thermocline and it wasn't instantly mixed, well, you'd have to simulate that lake using multiple mixing cells because mixing is not instantaneous. In a well-mixed, let's say, treatment tank, it may be a very good assumption to assume instantaneous mixing. So a single cell pathway is instantly mixed. And if you have any solids that have partition coefficients, the mass is instantly equilibrated between the fluids and the solids. We can impose solubility constraints inside a cell, and you're going to see that in a minute. We can have initial and boundary conditions in a cell. When Goldsim solves some cells hooked together, mathematically, it's equivalent to a network of finite volumes. We're going to actually form a system of equations and solve that matrix implicitly to calculate the mass and the concentrations. So in order to start to illustrate this, let's start with a very simple model. So in this model, I'm not simulating treatment at all. I'm just simulating mixing. I'm going to have water from two different upstream systems, say system 1 and system 2, enter a tank and then leave the tank. And all the tank is doing is mixing these two streams together. So let's open that model. That model looks like this. Again, here my upstream system actually just consists of two mixing cells. All right, but obviously this could be a very complex upstream system. It might be an entire mine system, for example, might have tens or hundreds of pathways in it. Here I've just said, here's our upstream system. One part of the upstream system has some iron and zinc, not Z, zinc in it, and another upstream system has the same two species but at a different concentration. So let's just see how we went about doing that. So here's our species, and I've just defined these two species in Goldsim. I haven't talked anything about their oxidation state or anything. I've just said I just have these two species, iron and zinc. All right, that's all we're going to talk about right now. And I have water in my system. My upstream mixing cell just contains some water, and I can actually specify a concentration. So in this particular case, I've said this mixing cell has water and it's got a defined concentration of 1 gram per cubic meter. This mixing cell has a defined concentration of 2 grams per cubic meter. Again, this was meant just to be simplistic. In a realistic model, you'd have an entire upstream system here that may have tens or hundreds of pathways that are feeding into this. So I've got water from these two upstream systems, and I want to put them into a mixing tank. And this truly represents a tank that's capturing this water and just mixing it and then discharging it. And I've got a flow rate from my upstream system. I'm outflowing from this mixing cell at a rate of 0.5 cubic meters per day. Same rate here, and obviously in order to conserve water, I'm leaving this tank at a rate of 1 cubic meter per day. So there's no dilution going on here. We're just mixing these two streams coming in. Very, very simple model. That's just, we're going to use this to now, after we look at this, to illustrate how we now can treat the water in the mixing tank. But right now we're not treating the water in the mixing tank. We're just mixing it. So if I run this model, and by the way, this mixing tank starts with no mass in it, right? So it starts empty. It's got 10 cubic meters of water, but there's no mass in it. So if we just look at the concentrations of iron and zinc, we get something that looks like this. Here's a concentration of iron. That's what's coming in. Remember, we said there was a constant concentration of 2 coming from one location and 1 coming from the other location. So obviously, if they're coming in at equal rates, once we reach an equilibrium, the thing starts at 0, we're going to be halfway in between, and that's what we see. So we just mix these two streams, so the water leaving the tank is 1.5. That's all we're doing here. Same thing with zinc. All right. So nothing fancy here. We're just mixing two streams coming into a system. And just to show you what Goldsim is actually solving, this is what it's actually solving. In this very simple system, that tank, there's actually an equation for each cell. But in this case, the equation for the tank just says the rate of mass change in the tank, right, it's what's coming into the tank, Q1, the flow from tank 1, or flow from upstream system 1 times the concentration upstream system 2 plus Q2 times upstream concentration 2 minus the flow out of the tank times the concentration in that tank. And the concentration of the tank is just M tank over the volume of the tank. Well, we can solve this, right? And that solution basically looks like that. All right, that's what we get. So very simple system. All right, nothing fancy here at all. All right, now let's talk about how we can do treatment. How are we going to model treatment inside this tank? So as I said, there's 2 ways that we can model treatment within Goldsim. The first way is to define a treatment efficiency. So very simple approach. We're going to say, look, we have some mass coming into a tank, and I want to remove 99% of it. I'm going to assume that magic happens in that tank, and 99% of this species is removed, and 95% of this species is removed, and 50% of this species is removed, right? We're not specifying what that magic is. We're just saying magic occurs, and this is how much mass is removed, right? That's the first way we can approach this. Second way we can approach it is we can say, I'm going to define some solubilities for the species. Once they enter the tank, some of the mass is going to fall out of solution based on the solubility I specified, and then I'm going to remove that mass from the system, the mass that's precipitated out of solution. So we're going to talk about these 2 different approaches here. As I said, there's a much more complicated approach that actually can be done in a variety of ways. You can actually do this more complicated approach kind of in a simplistic way, all the way up to coupling Goldsim to a geochemical equilibrium model. I will point to some examples of this approach number 3 that are in our model library, but I'm not going to discuss it in detail today. We're just going to focus on these 2 right here. All right, so let's look at approach number 1, defining treatment efficiency. So here's really what we're doing. We have this upstream system. We'll work with the same system I showed you for the mixing example. We have mass coming in from the upstream system and mass coming in from this upstream system. So we have some rate at which mass is entering the tank. Let's say grams per day, X grams per day and Y grams per day. What Goldsim is going to allow us to do is to define a treatment efficiency so that we're going to take what's coming in and we're just going to remove that and put it someplace else. Whatever remains then goes to our downstream system. So this is, we're not saying what happens, we're just saying, just remove this much mass. You know, if I've got a treatment efficiency of 0.99 and 1 gram per day enters the tank, 0.99 grams per day is going to be pulled out of the system, and the rest is going to move into the downstream system. So we're essentially going to, what we have to specify is this treatment efficiency, this fraction. It's just a fraction. What fraction of the mass entering is pulled out of the system automatically. So that's what this method entails. So how do we do that? Well, let's open the model that does that. So here's our no mixing model, and now let's open our model that has treatment efficiency. So we still got our same upstream system, okay? Now I've renamed this as a treatment tank because we're actually doing some treatment here. We still have 0.5 cubic meters per day from each of these two systems coming in, and then 0.1 or 1 cubic meter per day is going to my downstream system, which again may be an entire model here, right? I'm just going to send that mass in this direction, but then I need to remove some mass, and I have to put it somewhere. So this is mass that magically gets removed from the system, but I'm going to put it right here when I remove it. So how do I go about doing that within GoldSim? The way I do it within GoldSim is I have to define two different outflows. Right? I have my regular outflow where I went from my mixing tank to my downstream source. Right? Let's just look at that guy right here. So here's mixing tank, treatment tank to sink downstream. I'm moving 1 cubic meter per day of water. So that's exact same outflow we had in our mixing model. Nothing has changed there. We're just going to move. We're going to advect some water from here to here, and it's going to carry some mass with it. But what we're going to do that's a little bit different is we're going to add another link. We're going to add another outflow that's called a fraction of inflows. So how do we do that? Because this is a little bit troubling, a little bit confusing. I'm going to do this manually so you see it happen again. Okay, so I have my treatment tank. That's what we had before. I'm going to add a new outflow. Whenever you add an outflow, you have to specify where you're going to put it. We're going to put this into this thing called sink removed mass. Typically it says, well, what are you moving? What are you flowing? I'm flowing water. No, that's not what I want to do now. This is a special type of outflow. We're going to say, do a fraction of inflows. All right, we say fraction of inflows. And when we do that, when we have a fraction of inflows link here, we need to specify our treatment efficiency here, and that's what I've done. So now what's going to happen is I've just told GoldSim that sum up all the mass that's coming in and take 0.9 of the first species and 0.99 of the second species, that's my treatment efficiency, and send it to this mixing cell. The rest of the water just goes in this direction. Okay? Okay, let me just go back and okay. If we now run this model, okay, let's look at the concentration of iron and zinc. And by the way, my treatment efficiencies were 90% of the iron should be removed, 99% of the zinc should be removed. That's what I've told GoldSim. So that was the link right here. I had this outflow that says a treatment efficiency. It's a fraction of inflows type of link, and it has that treatment efficiency. So if I now look at my concentrations, what you see here is that's what's coming in, right? And that's what's leaving, right? And what you see here is for iron, it's basically 10% of it leaves, 90% of it gets thrown into here. If I look at zinc, 1% of it is able to leave, and 99% of it was removed and dumped into this guy right here. So that's what's happening here. You can see that here. What I'm plotting here is the rate in, the mass rate in to the mass rate out. And you can see that 10%, it's 10% for iron and 1% for zinc. So that's all there is to it. It's there's nothing. We're not telling GoldSim what's really happening in this tank. The tank is a black box. That's the way we should think about it. We're just saying we're just going to specify treatment efficiency. That's the mass that's removed here. And of course, if you wanted to, let me go ahead and rerun this model. You could keep track, which is what I'll do here. We can actually keep track of how much mass is removed from the system, which may be something you're interested in, right? So here I'm keeping track of how much mass of each of those two species is actually removed from the system via this magic treatment process. All right, so pretty simple approach, but in many cases, this simple approach may be appropriate for what you want to try to simulate. Just define a treatment efficiency. There's one really important point that you have to be aware of when you're simulating a treatment efficiency like that. And what that is all the incoming flows to the treatment tank have to be normal links rather than coupled links. What does this mean? All right, well, let me just show you that. If I look at this upstream system, I have an outflow from upstream system 1 that goes into the treatment tank at a rate of 0.5 cubic meters per day. So I'm going to delete that and recreate it. So I'm going to say I have outflow system, upstream system 1 goes into the treatment tank. By default, it says, well, what are you going to do? I want to move water. By default, it's going to be a coupled link. If you specify this as a coupled link, it will be ignored. All right, it will not be removed. I have to say it's a normal link. And when it's a normal link, now GoldSim, I've now told GoldSim, remove that mass if I use a treatment efficiency. So actually, you could actually use this in some way. If there was some reason why the mass coming from this direction was not removed, but the mass coming from this direction was, you could actually simulate that by saying this is a coupled link rather than a normal link. But this is something that people trip up on quite a bit, and I won't get into the math here of why it works this way. It's discussed in the manual, but basically this has to be what we call a normal link. Coupled links are not removed when they come in. The mass is not removed. It has to be a normal link. So just remember that when you're if you ever want to use one of these treatment efficiencies. Okay, so that's the first approach, a simple treatment efficiency. Now let's look at the second approach, and the second approach is we're going to define solubilities and remove precipitated mass. So this is a little bit different, right? So the first approach was we have a black box treatment tank in which we're going to specify how much incoming mass is removed. In this particular case, we're going to say the treatment tank is going to precipitate things out. We're going to change the chemistry, let's say, in some way, so that in the treatment tank I have some solubilities defined. And any mass that comes out of solution, I'm going to immediately remove from the system. The mass that is still in solution, which is basically going to be at the solubility limit, unless I have something else going on, is then going to flow downstream. So this is kind of schematically what we're doing in this case. All right. There's an important thing here is the solubilities are local. So I'm going to specify solubilities in this treatment tank. Those solubilities don't apply here, and they certainly don't apply here, and they may not apply here, right? So we're not saying that things are precipitating out of solution here. No, we're changing the chemistry here in the treatment tank. That's where they're going to precipitate out of solution. So in order to do that, we have to define what's called a local solubility. By default, the solubilities are global. You're going to see we're going to have to define a local solubility. So let's open that model and see what that guy looks like. So in that case, what we have is, again, the same system that you've been looking at before. We have these upstream mass coming into the system. But now I've had to do something a little bit different, okay? Instead of having my mixing cell just sitting there, I've put it inside a box. I've put it inside a localized container. And the reason I've put it inside a localized container, if I go inside that container, there's my treatment tank. You'll see I have water sitting right there. All right, I have water sitting there. I also have water sitting here. All right, so I have water defined in two places. So if you remember how local containers work, this local container, the things inside this container can't be seen outside the container. So water cannot be seen by these elements here. It can only be seen by that element, right? This water. And this water that's sitting up here can be seen by this element, and these other elements. This allows us to basically define a global solubility and then a local solubility right here. It turns out that this is a clone. So I can't define two elements named water, but I can define a clone. I've actually cloned this element, which is a kind of an advanced feature of GoldSim, but I've actually cloned this element to exist at this location. So if we look at water in this location, it says I have some solubilities. I'm going to link to something called solubilities. Inside the treatment tank, I've defined a solubility of 0.1 milligram per liter for iron and 0.01 milligram per liter for zinc. All right. If I go up here, I've also got a solubility. This water is the same. It's also looking for solubilities. It links to this guy. This guy specifies -1. And for those of you who have done contaminant transport modeling before in GoldSim, a negative solubility implies infinite solubility. So basically we're saying outside of the treatment tank, there is no solubility. We can hold as much of the mass as we want. Inside the treatment tank, inside this location, I'm going to apply some solubilities, 0.1 milligram per liter and 0.01 milligram per liter. So that's how we've set up our system. Okay, we've put if you look at the steps, we've cloned our water element, we've defined solubilities in each location, infinite solubility for the entire model, but then we're going to override that and define some specific solubilities at this particular location in the treatment tank itself. Okay, if we then look at our treatment tank, we've got an outflow to our downstream system. Again, we're just going to outflow 1 cubic meter per day, so that's what we had before. But now we're going to define another type of link called a precipitate transfer. And let me go ahead and create that guy from scratch. We're going to say I want to remove mass from the treatment tank and I want to send it to sink removed mass. it's going to default, well, what are you moving? Water. No, I'm not moving a fluid. In fact, I want to do something special. Before we had fraction of inflows, that was our treatment efficiencies. Now I'm going to say precipitate transfer rate. I'm going to click that, and then I'm going to specify a rate here. I'm just going to put in a number of 100. I'll explain this in a minute. So what this is going to do is when the mass enters this location, it's going to precipitate out a solution. Not all of it, right? There's still going to be mass left in solution. How much mass is going to be left in solution? Well, it's going to be at the solubility limit, right? The mass that entered, that precipitated out of solution, I'm going to flush into this location. I'm going to flush it at a particular rate. The rate I'm going to flush it is what I specified there. Basically, a big number here. Basically, this is a huge number. It's going to flush it all, right? There may be some physical reason why you can't flush this precipitated mass out instantaneously. You may have to do it in a slower rate. You can specify a slower rate here. But in this case, I'm going to say, no, as soon as it precipitates out of solution, let's assume it's removed. So I've just put in a big number here, all right? So when I run this model, we're going to get something that looks like this. All right, let's first look at the concentrations of iron and zinc. Okay, this is the concentrations of an iron and zinc coming in and leaving, right? So that's what's coming in. It's leaving at the solubility limit, right? Remember, the solubility limit for iron was, we specified 0.1, right? So that's what you're seeing here. And if we look at zinc, the solubility limit here is 0.01. So it's leaving at the solubility limit. All the rest of the mass got sent here. Right? It all got sent here, and we can actually see how much mass got sent there. That's how much mass got precipitated and removed from the system. So it's a different process than our kind of our black box treatment efficiency, right? And in fact, it's perhaps a little bit more physically based here. We're saying, we've got some process going on inside this tank that changes the solubility of what's coming in, and then I'm going to physically remove anything that precipitates out, right? So that's the simple process that we have going on there. So quite straightforward, quite simple. We're not really doing a lot of chemistry here, right? We're just saying, let's assume we're going to, inside this tank, magically make the solubility of iron B.1 and zinc B.01. It precipitates out a solution. By the way, this happens immediately. There's no kinetics here. As soon as it enters the tank, this is forced, and the concentration immediately drops to these levels, and any other mass drops out of solution, right? In this particular case, not only does it drop out of solution, but then we flush it to another location. Any precipitated mass is immediately flushed to this location right here. So two very simple approaches, all right? But you may start to get some ideas on how you can use this in your models. Before we kind of wrap up, I want to talk about this third approach. This third approach is, what if we actually wanted to model the chemistry properly? So we can integrate chemical processes directly into GoldSim, right? Here's a model that I'm going to show you in a second that simulates some of these chemical processes that are happening in much more detail than the simplistic way that I just showed you. If you're going to do this, however, obviously it's going to require some geochemical expertise and careful coupling of GoldSim to the external code. There's a lot of ways to couple this. If you go online, you'll see this this model, the series of model library models that were actually developed by Ted Erie. And in fact, I think I saw that Ted might actually be online here. He might be. I thought I saw his name pop up. So Ted developed a number of models and then graciously donated them to our model library. And they really illustrate how GoldSim can be used to kind of do these geochemical calculations. And this particular model library kind of walks through a whole bunch of examples that Ted developed. And they start simple and they get more complex. So I'm actually going to our model library right here, just for those of you who haven't visited it before. You can see what it looks like, and it looks like there we go. And so there's a series of models here, ranging from simple mixing all the way down to the most complex case where we're actually dynamically linking GoldSim to Freak-C, right? The model I'm going to show you actually doesn't go this far. It's a model that Ted developed that it actually uses some lookup tables constructed using Freak-C, but it doesn't actually link directly to Freak-C. So I'll show you what I mean by that. If we go back to this model, this is the model right from the model library. So what he's done here is he's got a series of tanks, right? They're carrying out various processes, aeration and adding lime and pH adjustment and so on. And in each one of these tanks, he's got a fluid. So this tank has a fluid called, aeration tank water. All right. Well, using Freak-C, he has developed and specified some solubilities for various species in aeration tank water. Okay, and they're just lookup tables, right? So for example, for aluminum, it's he uses this lookup table right here, which is a function of pH. And so for various pHs, he says this is what the solubility is. Right. So it's an approach to using an external code to be more realistic in terms of how you're modeling your chemical processes. The most extreme case, as I said, would be to link dynamically to a geochemical equilibrium model, which is also possible, and there's an example of doing that here. Again, I would just question, I'd come back and say, do you need to do that? Can you get away with one of the simple approaches we did, right? And do you really need to go to the next step of doing it in a very complex way? Because you're really increasing the complexity of your model by up to an order of magnitude or more by doing this linkage. So, you always want to do as simple as possible first. So the idea is, can we get away with a simple approach, a treatment efficiency or a very simple solubility, or do we need to go to the more complicated approach to model this treatment process? That's the question you need to ask you and your colleagues as you're approaching these problems. But as it is for all modeling, we want to stay as simple as possible unless that simple approach is inappropriate. But don't immediately assume that the simple approach is inappropriate. It might be quite appropriate. A simple treatment efficiency or a simple solubility may be good enough for what you're trying to accomplish, and you may not have to go to this much more complex step. So I will post this presentation along with all the model files. So the 3 model files and this, you've got the link to the model library, which is 6 more detailed model files. We'll post this up on our website probably by the end of tomorrow. So if you want to play around with the files that I showed you today, you'll be able to do that. If you have any questions about what we've talked about today, feel free to contact me, and we can chat about some of these things. Use our support desk for that. That way we can kind of, if you send an email to me, you may not get answered for a couple days. If you send to our support desk, one of us will answer it typically within an hour or two. So it's probably better to send it to the support desk rather than to send it directly to me. I may be the one answering, but it's always, we have multiple people monitoring our support desk. So that's really the best way to go. I would also emphasize again our model library, which I talked about here. This set of examples is just one of many that are in our model library. If you haven't spent any time there, I really encourage you to spend some time in our model library. You can kind of explore it. There's a number of water quality and contaminant transport example models that you can find. So here's the ones that have to do with water quality. So there's a number of interesting water quality models here that and some of these are quite detailed. So if you actually look at these models, you can learn a thing or two by just exploring a very complicated model. For example, here's a model of a lake that is quite complex. It's looking at nutrients in the lake, and it's got multiple layers, some mixing between layers. You may not be able to use this model directly, but by just playing with the model a little bit, you'll be able to learn some of the more advanced features of GoldSim. Some of the other models are quite simple. There's just some. Here's a simple mixing model that's similar to what I just showed. What I just showed you. So I encourage everybody to kind of visit our model library and explore the examples we have there. Okay, thank you for your time, and as I said, I will post everything that you've seen today, both the recording of the presentation, the PowerPoint, and the model files, and we'll have those posted on our website probably by end of tomorrow or maybe on Monday. All right, thank you very much for your attention, and have a good day.